So, we move on with today's material, right. So, now that we have defined all these random variables x and y and so on, right, what are the events that we can look at? Some events of interest. For example, you have the event x equal to y. What is the meaning of this? What is the meaning of x equals y? Why do we call that an event? It is just like we called x equal to k an event in the single random variable case, x equal to y will become an event in the two random variable or in the multi random variable case, right. So, this event happens whenever for example, in this case in the trinomial example, when the count of event 1 which occurs with probability p, right, equals the count of event number 2. I called them 1 and 2, right, yesterday. So, we have to continue with that. So, in the case of the trinomial, I mean okay, coming back to we put that on hold. So, in general, how do I calculate this? This has a probability, and we have already said that for discrete case almost, right, every event, every such combination of points in the space is an event, right. So, x equal to y is a valid event. I mean it's an event for which we should be able to write out the probability. And how do we write this? So, basically what you do is you look at the probabilities of these points x comma x, right, assuming that x comma this of course assumes that x comma x is a valid point in omega x. If there is no point x comma x in omega xy, then the probability of x equal to y is what? If I cannot, like for example in the drawing of the two balls, right, with different numbers x, you can never get x equal to y, right. So, in that case that probability will be 0, but in the trinomial case this is not going to be 0. So, in general what you do, you add up all these probabilities, right, with with equal arguments for x and y. So, that so this assumes you have at least one point in x in omega xy, otherwise the probability is really 0. So, when I say sum over x, I am talking appropriate values of x, right. You have to look at the situation, specific case, and see what the limit of the summation is going to be. So, in the trinomial case what happens? So, here we can draw this picture, right. This is the point 0 comma n. Here I am plotting the points I and j, and here I am plotting the points n comma 0, the points here. So, so this is the line I equals j, and we will assume without much loss of generality that what n is even, right. Why do I need so that it makes my job a little easier. So, this point I am going to assume belongs to the grid. What is this point? N by 2 comma n by 2. So, this is I equal to j line. So, what happens here? How do I write this? I do not have to keep, let me not take that and put it here again. I will just write it as pxy I comma I. You can anybody can substitute j for I out there, I am not going to do it for you, write it all over again. But what we are interested in this are the limits of the summation. What are the limits of the summation? What are the limits of the summation? Why 1? Why can't they both take the value 0? They can both take the value 0 also, no? It's possible that x does not occur or y also does not occur. Remember I said x and y are not event 1 and 2 are not a partition, right. It is not like you must get one of the two. So, you go from I equal to 0, what is the maximum value? N by 2 for n even. Okay. So, having understood this case x equal to y, remember, right, whenever you make statements about random variables, in general they are events. That is what I want you to remember, take away from all this discussion. Why should you look only at x equal to y? Why not look at x greater than y or x less than y? They are also events. Well, I may let me go here and go from here. The events of interest, right? So you have x greater than y, x less than y are also events, and that is why we write them with the curly brace. The curly brace notation is universally used to indicate events. So coming to this diagram, which is not all that well drawn, but we will have to live with it, right. The 45-degree line is a little skewed, but that is okay. So which portion of this diagram corresponds to the event that x is larger than y, and which portion corresponds to x smaller than y? That is exactly like going back to school, right. There is no only thing you have to remember, when you are looking at the probability of these events, you have to add all these probabilities. So these probabilities will give you what event? This is x greater than y. So this is and likewise this will be x less than y, and x equal to y does not fall into either of these two camps. It is distinct in the discrete case. So can find Px greater than y by what? You can say, well, Pxy, I have now in general I have a double summation. I have to say Pxy xy such that, so xy such that small x is greater than y. Strictly greater than y. So you have to add over all points in omega xy that give you the non-zero probabilities, and all those points where the x coordinate is bigger than the y coordinate. So this in general is a messy summation. It cannot be done easily, especially in the trinomial case. There is no nice closed form solution. Even here there is no nice closed form solution there also, but that does not mean the sum does not exist. I think I mentioned it in some earlier lecture. Existence simply means that the sum is finite, and here obviously all these probabilities have to exist. It is just that you can't write a closed form for it in terms of p and q and n. So you have to start getting used to the fact, right, that something can be a perfectly healthy number without being expressed in closed form. But what is the partition now? I have a partition of the xy space. What from sitting here? What is that partition? Right? There is a three-way partition sitting right in front of me. What is the three-way partition? These three events, x equal to y, x greater than y, x less than y is a partition. The sum of those three probabilities must equal 1, and they are exclusive. Only one can happen at any time. X less than y, x equal to y is a partition. Partition of omega xy. Now you can use certain symmetry arguments here, especially for x greater than y and x less than y. The symmetry argument may not work so easily for x equal to y, but it certainly in the sense that supposing I tell you that p must equal q, or p equals q, not must equal, p equals q. For p equals q, what can you say about the events x greater than y and x less than y? the trinomial PMF, let joint PMF, of course I am just omitting the word joint, but let P equal to Q. What can you say about x greater than y and x less than y? They must be, those probabilities must be equal, right, without even any calculation. Why can you say that with some great degree of assurance? Because in a probabilistic sense you are neither favouring event number 1 for which x is the count, nor favouring event 2 for which y is the count. So by symmetry the symmetry argument will come in very handy later on. Probability of x greater than y equals probability of x less than y. Of course this tells you nothing about probability of x equal to y, and so this tells you nothing about each of these individual numbers. It just so happens that these two are equal, and if you know this and if you know probability of x equal to y, it becomes trivial to find all three of them. Okay. So you should always be aware or try to exploit symmetry wherever possible. Okay. Now let us see one more type of PMF, conditional PMFs, right. Okay. In the one random variable case we also looked at conditional PMFs. How did we what kind of conditional PMFs did we consider over there? We considered some simple conditioning like x greater than x naught and so on. Here also we can do the same thing, but the type of conditioning which is more interesting here is if you observe, for example, that x takes a certain value. So here the conditioning events are conditioning event is, let us say x equal to x, which is, let us say, so an event of non-zero probability if for some x in omega x. In other words, you have observed that you have done the experiment and you observe that capital X has taken some value. What does that tell you about y? So you define, here when I say here I am talking of in the situation involving two random variables. So like this is what we take, or of course y equal to y is also equally typical. So we define the conditional PMF P of y given x. This is the notation we are going to use, right? Y vertical line x as a single subscript, argument y given x like this. So this x takes this value small x, and this is the argument of the PMF. So this is defined as this joint probability which comes from the joint PMF. Remember here y is the argument, so you are looking for probability. Okay, maybe before this I won't erase anything, but let me write this like this, and also write this as a conditional probability like this. Maybe I should have written this first and then this, but does not matter, right. Let me move away so that you can all see that the expression. Right. So why do I call it a PMF? I am going to allow the small y to vary while keeping the small x fixed. So, and what is y going to vary over? Of course, minimally you will want it to vary over all the points in omega y, but it turns out for example in this in cases like this trinomial, you may get a smaller range, you may not get the full range. If you know that x equal to x, y may not in many cases may not have the entire freedom to vary all the way that it did in the absence of that information. So y will have, so for some, I will say new omega y, which depends, this new omega y depends on the value of x. So in the trinomial case we will do this. Let's say x equal to I. In other words, what have we observed? We have observed that the event 1 has occurred I times. This is not, right, a typical algebraic statement of saying let the variable x take the value I. This is an event, remember again, right, last time I am saying it. When I say let x equal to I, it means the random variable x took the value I. Okay. Then what is the range of the, and obviously this I has to be in, it has to be in omega x, so it has to be between 0 and n in the trinomial case, it cannot be outside that. So given that x equal to y, what is this new omega y? Then the new omega y is what? If we in general depend on I, 0 to n minus I, right, set of integers for the, maybe I should have drawn that picture and kept it, but I can draw it again. If I say x is I, this particular I, that means I only have this much freedom for y, and so here I have the point I comma n minus I. I do not have the full freedom of allowing y to vary from 0 to n. Incidentally, this new omega y is my notation and you will not find it in books, but I have to call it something, so I am calling it that. I mean my terminology, right. But it is crucially important to freeze this before you proceed any further, because these are the values that you are going to allow for this y. So what is it? There is a reason for keeping all this, right, because we will need this, the expression. The nice thing about doing it on the board is something like this can stay, isn't it? So no flipping back and forth between slides, right? Okay. Px given y of, what did we call it? Sorry, y given x, right? Py given x of j given I. So I am going to still continue to use j here. So this is Pxy of ij divided by P, what is the denominator? Px of I, right. This is binomial, we have already worked it out. This is, therefore, the way to understand this conditional PMF is it is joint divided by marginal, joint by marginal. If you do the calculation, what do you think you will get? This has a nice closed form expression because there is no summation, nothing involved. You are taking this expression and dividing by, you are taking a trinomial expression with the same ij exactly put here, right. The understanding is j varies from 0 to, what is the variation of j? 0 to, this is the new omega y now, n minus I, right. So you vary j from 0 to n minus I. What will this come out to be? It turns out this is a valid PMF, right. This conditional PMF is a valid PMF. Note that it is always valid. If even before going any further, how do I know it is a valid PMF? If I add all these quantities, I should get 1, and that should be pretty obvious, because if I add all these points keeping x fixed and varying y, what do I get? I get back this, the denominator, right? So conditional PMFs are always valid PMFs. So in this case, so note that it's a valid right? It's a valid PMF once you consider it in totality, for all points j. What is the PMF that you get? What do you think? It turns out it's going to be binomial with what parameters? So this guy is binomial. Of course, n minus I, right? It's going to be that parameter, right? It's going to go from 0 to n minus I. So therefore, that n is n minus I, and the probability parameter, it turns out, is p divided by 1 minus q divided by 1 minus p. Not p, it's q divided by 1 minus p. Please do the division and work this out for yourself, because these kind of manipulations I do not have time for. I am just going to give the result and ask you to verify it for yourself. All you have to do is take this, divide by this, which is n choose I, p power I, 1 minus p to the power of n minus I, and it will neatly work out to be this. Please do it for yourself, right? And check. You can do it later on at home. I am not going to spend time on this here. So just to point out how this trinomial example is so useful in conveying all these concepts, that is why we take it up in some detail. Of course, the concept is far more general, and that is what is also very important. And in general, these conditional PMFs or conditional PDFs will keep coming up a lot in probability, because it says, right, given that, for example, the height is something, what is the distribution of the weight? If the height and the weight of the joint distribution that you are looking at, things of that sort, right. So it is a crucially important concept to understand, because we are not just interested in merely describing joint events and joint probabilities, we are also interested in observing something and asking questions of inference, right. The whole idea of statistical inference is based on observation. Okay. So clearly, I mean, you can also condition on, do the reverse conditioning, can also find, let me add that here. Similarly, find P of x given y. There is no sacrosanct reason why you must only condition on x. You can equally well condition on y, as the situation might be. And so you can define this dot given some j, if you want to call it, or small y in general. This again will be a joint divided by marginal, and I do not want to spend more time on it, right. So I think it should be fairly obvious how to calculate this. So when you look at it as a PMF, you put a dot here, and you look at the collection of probabilities, the countable collection with what all the possible values of this dot. That is why I do not want to put x. And in the case of this trinomial, what are you going to get? You are going to get once again binomial. This will become n minus j, right. If you said y equal to j, and what will happen to this? It will become p by 1 minus q. And note that this q by 1 minus p or p by 1 minus q has to be smaller than 1. Why? Because p plus q is smaller than 1. This must be smaller than 1.